In this calculus course, we've exclusively used Cartesian coordinates. What that means is that let's say we have a point in a two-dimensional plane. And so to locate where that point is, we go such a distance along one axis and then such a distance along a perpendicular second axis. Of course, Cartesian coordinates are named after the great French mathematician René Descartes. But we didn't have to use perpendicular axes. We could have used tilted ones. And in fact, there are thousands of different ways of representing a point in two dimensions. One way that we're going to talk about today is by using polar coordinates. Why use polar coordinates when you can use Cartesian coordinates? The answer is that it makes things much, much simpler sometimes. Let me first define what are polar coordinates. So suppose that this is some starting point. We'll call that O for origin. And this is a line that goes all the way to the right. Let this be a point P. And if we call this distance between O and P R, and this angle between the two lines as theta, then the polar coordinates of P will be called R and theta. We can, of course, choose this line over here to be the x-axis. We'll just call it that. In which case we can draw a line which is perpendicular to the x-axis, and what we'll get is the y-axis. So if you look over here, there is this distance which we call x, and this distance which we call y, and clearly x is r cosine theta, y is r sine theta. So given any value of theta and a value of r, x and y are fixed. Can we invert this? In other words, can we express theta and r in terms of x and y? It's very easy to do that. Let's divide this equation by this equation, in which case we'll get r sine theta over r cosine theta equals y over x, or tan theta is equal to y over x. And if we square these two equations and add them together, then we get r squared is equal to x squared plus y squared. That's clear from this diagram over here as well. Now there's one very important point that needs to be made. Every point P has got one and only one coordinate, x, y. But it has many r and theta. That's easy to explain. If I take theta and I add 2 pi to it, what that means is that I've gone all the way around once and come back to the same point. If I add 4 pi to it, then that means I have gone around twice. And in general, I can go around 2n pi and come back to the same point here. Or of course, I could go in the other direction. In other words, theta minus 2 pi. Obviously, these are all different angles, but they all correspond to the same point P over here. There's a second important point. We shall always take r to be positive. You see over here from r squared equals x squared plus y squared that there are two possibilities. R is plus or minus x squared plus y squared. Well, we shall never take the minus sign. We shall always take r to be positive. And of course, nothing is lost by taking this condition. So suppose that one wants to come to this point over here, which I'm drawing over here. That means that we would simply add pi to theta, and this angle from here all the way over here will be theta plus pi. That will get us to a point which is directly opposite to this point here. So even with r greater than 0, we can reach every point in the plane using the condition r is greater than 0 and theta being between 0 and 2 pi. Let's first see how these ideas work out for a simple example. We've been asked to find the polar coordinates of the point P, whose Cartesian coordinates are x equals square root of 3 over 2 and y equals 1 over 2. We'll calculate r squared, which is x squared plus y squared. That's 3 over 4 plus 1 over 4, which is 1. And remembering that we take only the positive root, we get r is plus 1. What about theta? We can see that tan theta, which is y over x, is 1 over 2 over square root of 3 over 2, and that is 1 over square root of 3. Now, which angle theta has a tangent of 1 over square root of 3? That is theta equals pi by 6 or 30 degrees. But to this, you could add, of course, any multiple of 2 pi. So if you add to this 2n pi, that too will have a tangent which is 1 over square root of 3. In other words, if this theta is pi by 6 or 30 degrees, you would go around once, twice, 3 times, or you could go in the other direction. Let's now see what happens when the Cartesian coordinates are a little different. So here, x is the same as before, but y is now minus a half. So that's the y over here. Here is this new point. It has y now as minus a half, and so we are asked to find the value of this angle over here. Now, we can immediately recognize that because tangent of minus theta is minus tangent of theta, theta is therefore minus pi by 6. So you could say that if we go off in this direction, that is to say, if we go clockwise instead of anti-clockwise, then we will have to go through an angle pi by 6 in this direction. If we add 2 pi to this, then let's see what happens. If I add 2 pi over here, that will have the same tangent, but now the value will be 11 over 6 pi, and both this and this are correct answers. How to interpret this? Well, that's the angle that we would have to go through in this direction, and this angle will be 11 over 6 pi. We'll now learn to plot curves using polar coordinates. This will help us understand why polar coordinates are useful in many situations. Let's first plot the curve r is equal to 2. Now, here there is no mention of theta at all. That means that every point on this curve has simply got to have r equal to 2. So this point, which is at theta equals 0, or this point, which is at theta equal to pi by 2, or this point, which has theta equal to pi, and so forth. And, of course, points that are in between as well, like this. So every point joined from the center has a distance 2 from this origin. If we join them up, then, of course, we get a circle. Now, notice how simple this equation of the circle is. Just to see that we understand this well enough, let's square this. So we get r squared is equal to 4, which means that x squared plus y squared is equal to 4. And now you see this is a quadratic. This is
the equation of a circle with radius 2 as well, but this is more complicated compared to this. Let's now take another example. Here we are asked to plot the curve r is equal to 2 over sine theta. Now, instead of giving different values to theta and looking at different values of r that result from it, what I will do is simply write this as r sine theta equal to 2. But r sine theta is y. So y equals r sine theta is 2, but y equals 2 is this straight line. It's independent of x and has value 2 for every value of x. Now, this equation, y equals 2 and r equals 2 over sine theta, they are, of course, giving you the same curve, but in this case, the Cartesian equation, y equals 2, is the simpler one. On the other hand, for the case of the circle, this r equals 2 was the simpler one. Another example. Plot the curve r is equal to 2 cosine theta. It's not immediately obvious what it's going to look like, so let's give theta different values. Theta equals 0, r is 2 cosine of 0, which is 2. If I put theta equal to pi by 3, then r is 2 times cosine of pi by 3, which is a half, so this is 1. If I put theta equal to pi by 2, then r becomes 0. If I make theta go to minus theta, in other words, if I put minus pi by 3 or minus pi by 2, it will not change the value of r. R will go into r. Let's now see what this curve looks like. Starting from 2, the value of r decreases, goes to 1, then goes to 0 at theta equals pi by 2, and then starts increasing again until it reaches 2 again. It's clearly a circle which is centered at x equal to 1. Actually, it's quite easy to see why it is a circle. If we take r equals 2 cosine theta and multiply with r on both sides, we get r squared is 2r cosine theta. But r squared is x squared plus y squared. And this is equal to 2 times r cosine theta, but r cosine theta is x. So we have x squared minus 2x plus y squared equals 0. But now I can complete squares and write this as x minus 1 squared, and then I have to subtract from this 1 plus y squared equals 0. And so we end up with the equation x minus 1 squared plus y squared is equal to 1 squared, or just 1. And this, of course, is the equation of a circle which is centered at x equals 1, in other words, over here, and which has radius 1. We'll now plot the curve r is 1 minus cosine of theta. If one gives different values to theta, starting with 0, r will be 0. Theta equal to pi by 2, r will be 1. Theta equal to pi, at which point cosine of pi is minus 1, r will be 2, etc. And of course, if you make theta go to minus theta, that does not change cosine of theta, and so r remains unchanged. R goes into r. So there is definitely a symmetry. But then this curve, it turns out, is not going to be so simple. In fact, the Cartesian equivalent of r equals 1 minus cosine of theta is going to be this. Let's just check that before we plot the curve. So this over here I'm going to write as x squared plus y squared squared. So that's the first 3 terms in here. Then I'll take 2x common, and here is x squared plus y squared, and then there's minus y squared equals 0. X squared plus y squared is r squared, so that's r to the fourth plus 2x r squared minus y squared. And now instead of y, I'm going to write y equals r sine theta, and instead of x, I'm going to write r cosine theta. So here we have minus r squared sine squared theta. And now let's put over here x as r cosine of theta also. So this equation becomes r to the fourth plus 2r cubed cosine of theta minus r squared sine squared theta is 0. Well, let's get rid of the r squared. Just remove 2 of the r squareds. So this over here becomes r squared. And so what we have is r squared plus 2r cosine theta minus sine squared theta, but sine squared theta is 1 minus cosine squared theta, and that's equal to 0. So we can write this as r plus cosine of theta squared. That's because here I have plus cosine of theta squared. And so that is equal to 1, which means, of course, that r is 1 minus cosine of theta. Now you see over here that this is quite simple looking, whereas this over here is quite complicated. It's a quartic, 4 powers of x, 4 powers of y. You can see that this curve is indeed quite complicated. Starting from theta equals 0, r equals 0, it has gone through quite a change. It is symmetrical as theta goes to minus theta, and you can see that it is symmetrical on the upper and on the lower sides. Therefore, this kind of a curve is called a cardioid. The cardioid is well known to those who deal with microphones. This is a cardioid microphone polar plot, that is in polar coordinates. The microphone has to be most sensitive to the sound that comes in from the front like this, and it has to be least sensitive to the sound that comes in from the back. And that is reflected over here in this cardioid microphone polar plot. So here is the sensitivity as a function of angle. Here is the curve r equals cosine squared theta. You can see that this too has a fairly interesting kind of shape. You notice over here that because we have cosine squared of theta, r is always positive, as it indeed should be. At theta equal to 0, r is at its maximum, meaning 1. At theta equal to pi by 2, it is 0. This is actually how electrons are distributed inside a hydrogen atom. By now, you might have gotten the impression that if I make theta go to theta plus 2 pi, I always come back to the same coordinates. That is not necessarily true. Although we did see that it was true for a circle, but this example, where we are asked to plot r equals e to the theta by 20, will show that that is not always true. Here, if I make theta go to theta plus 2 pi, then e to the theta by 20 will go to e to the theta by 20 times e to the 2 pi by 20. Now, if I increase theta still further by 4 pi, then it'll go to e to the 4 pi by 20, etc. So you can see that in this case, r equals e to the theta by 20 is going to be something that will increase and as theta increases, r will just keep increasing and increasing like this. But now let's plot this properly. I'm going to start off this plot by taking theta to be very large and negative, which means r is small, but then as theta becomes less negative, in other words, as it increases, you see that r begins to increase, and it increases, and goes off into this spiral. Let's look at it again. You see that as theta gets larger and larger, the radius of the spiral, that is to say, the distance of any point on it, becomes larger and larger and larger until it goes off the screen. To get the rough shape of a curve, it's not necessary to have a computer or even graph paper. One can use quite simple reasoning. So, for example, let's take this curve and see if we can get the outlines of this using just a few points. So let's put theta equal to 0, in which case r is 2 over 1 plus 1, and so that's 1. If I take theta equal to pi by 2, so theta has increased from 0 to pi by 2, and r has now become 2. Now take theta approaching pi, and as theta approaches pi, cosine of theta approaches minus 1, so r approaches infinity. If I take either plus or minus pi by 2, or plus or minus pi, it makes no difference because cosine of theta is an even function. Now let's get the shape of this curve. So if I take theta equal to 0, which is a point here on the x-axis, then this distance is 1. As theta increases and goes up to pi by 2, we get to r equal to 2. And now on this side, we also have 2 over here. So r equals 2 here. And so the shape of this curve has already come to us. It's going to look something like this, going off to infinity as theta increases. But before plotting it properly, let's ask what is the Cartesian equivalent. So let's write this now in the form r plus r cosine theta equals 2. But r cosine theta is x, and so we have r is equal to 2 minus x. Now square both sides, so we get x squared plus y squared equals 4 minus 4x plus x squared. The x squareds cancel, and so y becomes plus or minus 2 times square root of 1 minus x. This part over here is plus 2 times square root of 1 minus x, and this part here is minus 2 square root of 1 minus x. As I had remarked earlier, this is not a function in the sense that a given value of x does not give you a unique value of y. It gives you two values of y, plus or minus 2 times square root of 1 minus x. Well, now let's plot this. Theta is increasing from negative values. When theta becomes 0, you see that r becomes 1. When theta approaches pi by 2, this becomes 2, and then it goes off to infinity. So this is exactly what we saw earlier. Now that we've plotted a number of different curves, we can ask how to calculate the slope dy by dx of a curve that's given in the form r is some function of theta. Now what that means is the following, that suppose we have a straight line, we'll call this the x-axis, and there is some curve which looks like this, that's r equal to function of theta. If you take a point on this curve, this is at a distance r, this makes angle theta. As theta increases, this point over here is going to move to a neighboring point here. And what we want is the slope of this line, and that's going to be dy by dx. Now, let's remember that if y is a function of x, then x is a function of theta. As you change theta, both the x and the y's change. Let's now ask how to differentiate y with respect to theta. Well, by the chain rule, this requires that we differentiate y with respect to x and x with respect to theta, which means from here we get dy by dx is dy by d theta divided by dx by d theta. However, we know that y is our sine theta, which means that we can differentiate y with respect to theta, remembering that r is itself a function of theta. So we have dy by d theta is dr by d theta into sine theta, and then you have to differentiate the sine theta, keeping r constant, so we get r cosine theta. Similarly, if you have x is r cosine theta, then from here dx by d theta requires that we differentiate r with respect to theta, keeping cosine theta unchanged, and then differentiating the cosine theta gives minus r sine theta. So now we have our formula, what we were looking for, that dy by dx then is dr by d theta sine theta plus r cosine theta divided by dr by d theta cosine theta minus r sine theta. So the basic point over here, and this is the answer that we were looking for, is that theta must be thought of as an independent variable. As theta changes on this graph, this point moves first here, then could move here, whatever. But this curve is determined by giving the value of theta. Let's now see how the formula that we just derived for dy by dx works out for the curve that we just plotted, which is r is cosine squared theta. So let's work out dy by dx. We have to differentiate r with respect to theta. That gives 2 cosine theta sine theta with a minus sign, and then we have to multiply by sine theta, so that's sine squared theta. And here we have cos cubed theta divided by, again, minus 2 cos theta sine theta, but we have to multiply by cosine theta, so that's cos squared theta, and here we will have cos squared theta sine theta. Let's divide out by cosine theta. That will slightly simplify it. So we have minus 2 sine squared theta plus cos squared theta, which I'm going to write as 1 minus sine squared theta. And at the bottom, we have minus 3 cosine theta sine theta. And let's just write this as 3 sine squared theta minus 1 divided by 3 cosine theta sine theta. Now there are several points to note over here. Firstly, when theta is 0, or it is pi, or it is 2 pi, we'll have dy by dx. You can see that the numerator will be minus 1, and it'll be divided by, over here, 0. So it's minus infinity. What that is saying is that at this point here and at this point here, so that's theta equals 0, this is theta equals pi, and of course 2 pi is the same as 0. In that case, the derivative goes to minus infinity. And you can see that that is obviously true because here the slopes are infinite. What about at, let's say, a point where the slope is 0? Then we'll have 3 sine squared theta minus 1 equal to 0. And that means sine theta will be plus or minus 1 over square root of 3. So these are the points where the slope is 0. So here, 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 and here. The angle theta, which has sine equal to 1 over square root of 3, is, for example, this one over here. This is simply to check that the formula we derived actually makes sense. We'll now calculate the length of a curve that's given to us in the form r is some function of theta. So let's draw an arbitrary curve. So it could be looking like this, and take 2 points that are close together. So let's say this little bit of line between them, this length we shall call ds. Here is a point, we'll call that r theta. And then when theta changes, then r also changes, and we go to this point. So you could call this r plus dr theta plus d theta. Well, let's write it down like this: r plus dr theta plus d theta. Now, let's blow up this little part over here, ds, make it look a little bigger. Then what we have is dx and dy. And from the Pythagoras theorem, we have ds squared is dx squared plus dy squared. Let me divide both sides by d theta squared. So ds by d theta squared is then dx by d theta squared plus dy by d theta squared. Let's now look at this issue in the following way. X is a function of theta because x is r cosine of theta, and of course r is itself a function of theta. So as theta changes, so as let's say we go from r theta to r plus dr theta plus d theta, obviously r has changed. Now let me take dx by d theta over here. So that's dr by d theta into cosine theta. And then I leave r alone and differentiate cosine theta, so I get minus r sine theta. Similarly, y is r sine theta, and so dy by d theta will be dr by d theta times sine theta, and then I differentiate sine theta, keeping r constant. So that's r cosine theta. And so ds by d theta squared, I'm going to put dx by d theta and dy by d theta into this formula. That becomes dr by d theta squared into cosine squared theta minus 2r dr by d theta cosine theta sine theta, and then r squared sine squared theta. Now I have to add to this dy by d theta squared, and that's coming over here. So that makes sine squared theta. And here the difference is that we have plus 2r dr by d theta cos theta sine theta, and here comes r squared cos squared theta. Now clearly this and this cancel. Also dr by d theta squared can be taken common, this cos squared theta plus sine squared theta, which is 1, and similarly here r squared has sine squared plus cosine squared theta. So this then gives us dr by d theta squared plus r squared. And so we have the important result that ds by d theta is then the square root of dr by d theta squared plus r squared. Now, that was just this little bit of line over here, ds. If we want the total length s, all the little pieces have to be added up together, and that then tells us that we have to integrate over theta from whatever starting point there is to whatever end point that there is. And instead of ds by d theta, I'm now going to put the formula that we derived, dr by d theta squared plus r squared. And this is the formula which will tell us the length of the arc between theta 1 and theta 2. So if, let's say that theta 1 is here and theta 2 is, let's say, here, then we would integrate from this value of theta to that value of theta. Let's quickly apply the formula that we've just derived for the length of a curve. First, for the curve r equals 2, we are asked to find the arc length between theta equals 0 and another angle, theta equals phi. Of course, this is just a circle of constant radius 2, and this is the angle phi. We are asked to find out this length. That is to say, if we go from here to here. Since r is a constant, dr by d theta is 0. And so s is the integral over theta from 0 to phi. And since square root of r squared is r and r is 2, then s becomes simply 2 times phi. Of course, if phi is 2 pi, then we'd get s equals 4 pi, and that would be the circumference of a circle of radius 2. Now that was very simple and the right way to do it, but here I'm going to take a curve which really one should not look at in polar coordinates, but if one still decides to do so, nevertheless, you can get the right answer. So here, if you remember, this is r sine theta equals 2, but r sine theta is y, so we're really looking at the curve y equals 2, which is a constant line like this. The angle theta equals pi by 4 is this, and the angle theta equals pi by 2 is this. So let's first calculate dr by d theta. That is obviously 2 over sine squared theta cos theta, and there is a minus sign. So now let's calculate s, which is the integral over theta from pi by 4 up till pi by 2 square root of dr by d theta squared, which is 4 cos squared theta divided by sine to the power 4 theta, and then r squared is 4 over sine squared theta. Let me take this 4 over sine squared theta out, so that becomes 2 times integral d theta, and we have 1 over sine theta, and then square root of cos squared theta divided by sine squared theta plus 1. And now this square root factor is simply 1 over sine theta itself, so this is 2 times integral d theta 1 over sine squared theta, and of course we're going from pi by 4 to pi by 2. The integral of 1 over sine squared theta is simply minus cotangent theta. And you can check this by simply differentiating. So this is minus 2 cot theta between pi by 4 and pi by 2. When theta is pi by 2, cotangent of pi by 2 is 0. And when theta is pi by 4, you get cotangent of pi by 4 is equal to 1. And so the answer is 2. Of course, that's exactly the right answer, because this length from here to here, so this length over here, is indeed 2. And we didn't need to do an integration to prove that, but since we decided to use polar coordinates, it became more complicated and we had to go through it all. We can use polar coordinates to calculate areas as well. For some situations it is advantageous and for others it is not. For a circle, of course, it is very advantageous. So let's look at a portion of a circle and call this angle over here as delta theta. So that's this angle. This area will then be a fraction of the total area of the circle. The total area of the circle is, of course, pi r squared, and the fraction of the area that we've covered with this shaded area is delta theta over 2 pi. So if delta theta was 2 pi, we'd get the whole area of the circle. And this is then half r squared delta theta. In this case, r is constant. But let's say that we had a curve like this, in which r was not constant. So something like this maybe. In which case, if we looked at this little bit of area, that would indeed be the same. That is to say, it would be half r squared delta theta, or if it's very, very small, d theta. But now r can depend upon theta. If we want the area which is between, let's say, theta 1 and theta 2, we'll simply do this integral half r squared of theta, of course. And that would be the area between theta 1 and theta 2. As an application of the area formula, let's use this to get the area under half a cardioid. So let me increase theta from 0 all the way up till pi and stop over here and ask, what is the area under this red curve? Applying the area formula that we've just derived, that area is the integral over theta from theta equals 0 to pi of half r squared. And now, since r squared depends upon theta, we've got to take that into consideration. So let's just expand this. This is 1 minus 2 cosine theta plus cosine squared theta. But the integral over cosine theta between 0 and pi is 0. Why? Well, just remember this, that if you have the cosine curve, the area here will cancel the area here. And so we have only to do this thing, d theta between 0 and pi, 1 plus cosine squared theta. But cosine squared theta is half into cosine 2 theta minus 1, or rather plus 1. And now you can see that this is just half, and then there's 1 plus a half, which is 3 over 2, integral d theta from 0 to pi. And there is this integral over cosine 2 theta, but the integral over cosine of 2 theta will also be 0. And so that's then 3 over 4 times pi. That is the area which is under this red curve over here. That's half a cardioid.
I think it's pretty clear by now that some expressions and some equations get much simpler when you write them in polar coordinates in 2 dimensions, which is what we've discussed so far. But if you go to 3 dimensions, you can also define polar coordinates, and we shall do that at a later time. And in that case, the simplification is even more dramatic. In fact, there are many problems in physics that would be very, very hard to do unless we invented these polar coordinates in 3 dimensions.